Okay, so yeah, let me connect with my another computer. Uh, is Navin there?
Yes, sir.
Ah, okay. So I'm actually like I would like to share it in my another computer. I'm joining 1 minute.
Yes, sir.
Hi, can you allow this Venkatesh Rajendran to share the screen? You can make me co-host here.
Yes, sir. 1 minute, sir.
Hmm.
Yes, sir.
Yeah, okay. So let us start the meeting. Okay, I guess a couple of students are there. So uh, we need KR. Like, so you guys have any questions that you would like to ask related to the? You guys are there?
Yes, sir.
Damodiran?
Yes, sir. Good morning, sir.
Yeah, good morning. Yeah.
Sir, please provide the solution for the assignment that has been submitted, sir.
Please provide solution for the.
Assignment that has been submitted, sir.
You have already submitted.
Yes, sir.
Assignment 7. So we need to know which question that you are interested in. You have any specific question or you want solutions for all the problems? Hmm? Sorry, Vineet, could you explain? Like, are you interested in any specific problem? Are you there?
Yes, sir.
I didn't get your question. Are you interested in any specific assignment problem, or you want solutions for all the problems?
Sir, assignment number 7.
Okay.
First question, sir. Please explain, sir.
First question.
Yes, sir.
Okay. Okay, give us 1 minute because we are just getting back that question. Okay. So,
Okay, sir.
yeah, you see the screen, na? So you are actually
Yes,
talking
sir.
about that two linear operators T1, T2 having some particular minimal polynomials. Is that the question? It is assignment 7 first problem, na? Okay, so I will
Yes, sir.
hand it over to Satish, who will explain that. Okay, he's our TA. Yeah.
Okay, Vinit. So let me just repeat the question again. So if you have two linear operators T1 and T2, such that the minimal polynomial of T1 is x minus 2 times x minus 3. Okay, so what does this, let me ask you a question. What does this say about the eigenvalues of T1?
2 and 3.
2 and 3, right? But do you know something about the multiplicity of the eigenvalues 2 and 3?
Yes, sir.
Huh? What are the multiplicities of 2?
Write down it is operator from R3 to R3.
Yeah,
R3 to R3.
Yeah. So,
R3 to R3. So it's a 3 by 3 matrix, right?
Yes, sir.
And there are at least two eigenvalues, namely 2 and 3. Now, what can be the multiplicity of 2?
But
Multiplicity of the eigenvalue 2 can be
either 2 or 1.
either 2 or 1. Correct. Similarly, for 3, it is
Either
either
2
2
or
or
1.
correct. So let me write it like this. I'll write 2 comma 1. So by that I mean if the multiplicity of 2 was 1, then the multiplicity of 3 is forced to be 2, right? You agree with that?
Yes, sir.
Yeah. Now T2 has the following minimal polynomial. What is it? It is x2, sorry, x minus 2 square times x minus 3, right?
Yes, sir.
Now, what can you say about the eigenvalues of T2?
Eigenvalues are 2 and 3.
2 and 3, correct. again 2 and 3. But now, what is the multiplicity of 2?
Multiplicity of 2 is equal to 2.
2, right?
Yes.
And so, what could be the multiplicity of 3?
31.
2, 1 illa. No, no, just think carefully. So, this is a 3 by 3 matrix. Already, there are two generalized eigenvectors for eigenvalue 2, right?
Yes.
So, multiplicity of 3 can be 1, right?
Yes.
It is forced on us, right?
Yes.
Yeah. So, in the question, it is given that A2 is the multiplicity of 2 for the operator P1, A3 is the multiplicity of 3 for the operator P1. Similarly, B2 and B3 for operator
B2
P1.
and B3.
Right. Now, what are the questions? What are the options that you have? Uh, can B2 and B3 be 1 at the same time? No, right? We have seen that B2 is exactly 2.
Yes.
Okay, so option A is wrong. Do you agree with that?
Sir, B2 is equal to 2. How, sir?
So this is the minimal polynomial, right?
Yes, sir.
If you write the Jordan canonical form, then it will have. So the Jordan canonical form for T2 will be what?
Okay, the minimal polynomial divides characteristic polynomial. Na? But what is the degree of the characteristic polynomial?
Exactly.
3.
The degree of the characteristic polynomial is 3. But the minimal polynomial already has degree 3. The degree 3. So that will force what?
Sir, please explain generalized eigenspace, sir.
No, that is not needed. Venkatesh sir was saying something more elementary. He says uh, minimal polynomial divides characteristic polynomial,
Yes.
right? And characteristic polynomial ka degree is 3. But here the minimal polynomial's degree is also 3.
Yes, sir.
And characteristic polynomial is a monic polynomial, right? So that
Yes, sir.
forces the minimal polynomial is equal to the characteristic polynomial. Do you agree?
Yes, sir.
Yeah. So what is the multiplicity of the eigenvalue 2 in the characteristic polynomial?
2.
2, right? Yeah,
Yes,
that
sir.
is what is B2. Okay, so wants to know what is the definition of generalized eigenvalue.
Generalized eigen space, you haven't seen the definition. So given, let's say, some lambda, okay, which is like some element of the field, okay. So here the ground field is R. So then you call this V lambda, which is the generalized eigenspace, capital V. So this capital lambda, you can take it to be those vector in V such that, yeah, this is, okay, V is my R3. So you can take this operator, okay, let's say I'm fixing the operator to be T. Then T minus lambda
And
I power some K should kill this V for some K. Okay,
yes, sir.
and if this is non-zero, then this you call is generalized eigenspace associated with lambda. Okay,
Yes.
so yeah, so then you know this what is called Jordan decomposition, but all those things are not needed here. Here you are given some minimal polynomial information and the of two operators, and then you are asked to compare their multiplicity. So the second operator has the minimal polynomial which is already degree 3. So because minimal polynomial divides characteristic polynomial and minimal polynomial being monic, so it has to be same as characteristic polynomial up to some scalar. But anyway, we are only worried about the multiplicities of the roots, which is also like dimension of that particular thing. Nah? So then the multiplicity of 2 is going to be 2, which is B2. Multiplicity of 3 is going to be 1, which is B3. So B2, B3 must be 2 and 1. But A1, A2, A3, those things have some choices.
Yes.
But once you fix some multiplicity of 2, then the multiplicity of 3 is fixed. Okay?
Yes, sir.
For example, multiplicity of 2 is 1, then the multiplicity of 3 is forced to be 2. Because they have to add up to the degree of the characteristic polynomial.
Yes.
Okay? So now you can go through the options A, B, C, D and then pick up the correct thing. For example, the first option B2 equal to B3 equal to 1 is not true. Okay.
Yes, sir.
The second option B2 equal to 2 and then A2 equal to 1. So can it happen?
A2 is equal to 2 choice, 1 or 2.
Yeah.
Yeah, but A2 equal to 1, can it happen? If A2 equal to 1, then that forces A3 to be 2.
Yes.
Okay.
Yes, sir.
So now, like, yeah, whether B2 can it be 2? That is the question. So B2 equal to 2 is already we know. Okay, B2 equal to 2 and B3 equal to 1, both are fixed.
Both are forced.
Forced actually. Yeah.
But A2 is not necessarily 1, right? So can you give a linear operator on R3 with minimal polynomial x2 minus sorry x minus 2 into x minus 3, but the multiplicity of the eigenvalue 2 should be 2. Can you give such a linear operator, or can you give such a matrix with eigenvalue 2 coming twice and eigenvalue 3 coming once?
So what if you take this diagonal matrix 2, 2, 3?
Yes, sir.
So what is the minimal polynomial of that?
1, 0, 2.
2, 2, 3. Yeah, this is the, let's say, matrix. What is the minimal polynomial of this?
X minus 2, X minus 3.
Yeah, exactly. But what is the multiplicity of 2?
Multiplicity of 2 is
2. Yeah. So the second option is also not correct because A2 can be 2. Okay. So
yes.
now go to the third option. Third option, again, it says that A2 is less than or equal to B2, which is always true because B2 is 2. But it also says A3 is B3. Can it happen?
A3 is 2 choice, sir. 2
Yeah.
and 1.
So again, like you can take the matrix 2, 3, 3, na?
Yes, sir.
On the diagonal. That will have multiplicity of 3 is 2. So that means C is also not correct. So now go to D. Is that correct? So A2 less than or equal to B2 is correct. Now A3, you look at it. A3 is always, it is either 1 or 2, which is going to be greater than or equal to B3. So only the option 4, D is correct. Okay?
Yes.
Yeah. Anything else? Yeah. Yeah, Damodaran. Yeah.
So I have some sequence of things.
Yeah, tell us.
So the first one was the we can decompose our representation as a irreducible one. A direct sum of
Which
any given SL2C representation.
SL2, yeah, okay.
From that last week, how many that irreducible component, how many times that irreducible components will occur? We have to find through the dimension of the eigenspaces, H eigenspaces.
Yeah.
And,
Second question.
and yes, actually, in this week, 7th week, fourth problem it is.
Fourth. Okay, fourth. Yeah.
From that, the that irreducible components taken as multiplicity.
Okay, the multiplicities are given. Using
Yeah.
that, you are asked to actually
Sorry.
count the multiplicity of the irreducible components.
Yes, sir.
Yeah. So you want to know how to do that.
No. I find that whether we taken including that multiplicity. Actually,
No, only the weight and
irreducible
multiplicity information is given. This is the fourth problem that you are talking about.
From that fourth problem, the question asks how many times that irreducible component
Yeah,
occurs.
V of 0 occurs, V of 3
Yes,
occurs. Yeah, exactly.
yes. From that, the answer of
Yeah.
the V0.
Answer is A and C, both are true actually. V of 0 will occur twice.
But
V of,
the zeroth eigenspace
yeah.
will occurs in both the irreducible representation V2 and V4, sir.
Yeah, correct. Yeah.
Also in V0 also.
That is true. Yeah.
So the H eigenspace of the eigenvalue 0 here in the V0, the dimension is 5, and V2 dimension 3, V4 dimension 2.
No. You are misunderstanding.
Sir?
So it just says in V, the dimension of the eigenspace 0 is 5.
Yes, sir.
It's not on V0.
V. Okay.
You are given capital V. Okay. This is the SL2C representation.
Yes, sir.
So here you are given a table. Okay. Let me
Yes,
write down the partial table. So on the top you are given the weights. The 0 weight if I take inside capital V, then the multiplicity of that, the dimension of V0. Okay, this is 5.
Okay. Yes.
So this is that zeroth eigenspace of the operator H. Okay. So basically, what is V0? V0 is those vector V in V such that H dot V is 0, where H is the element of the basis, the SL2C.
Yes, sir.
So this is that 1 minus 1. This element. You know that H will act diagonally on capital V. So you can write V as direct sum of eigenspaces. Okay.
Yes.
So the information that is given, the zeroth eigenspace will have dimension 5. Similarly, what is given the weights? Okay, let me write it everything. Weight will be minus 5, minus 4, minus 3, minus 2, minus 1, and then 1, 2, 3, 4, 5. Okay, this is the table. So minus 1 will occur 8 times, and because of the symmetric, 1 will occur 8 times. Okay, if 2 occurs 3, and then minus 2 should occur 3. So only I am allowed to only fill the one side enough actually, because there is this symmetric. Okay, so then the other side is also filled similarly. 6, 2, 6. But if you are interested in finding out SL2C decomposition, okay, the way you find out, first start with the maximal weight. The maximal weight will be what?
Here actually
It is
5,
actually
sir.
5.
5.
Okay. 5 and 4. Why?
Okay.
5 is
Yeah.
yeah. So 5 is the maximal weight. So then definitely V5 occurs inside V. Okay. But if I take 5, na, but what is the dimension of that five eigenvalue 5 weight space? That is 6.
6.
Okay, so that means 6 copies of V5 should occur. Na? So V5 direct sum 6 occurring in V. But if I take V5, what are all the eigen values? -5, -3, -1, 1, and then what? 3, 5. So each one will occur with 6 of them. This 6, this 6, this 6, this 6, this 6. So these many things are actually vanishing. Okay. So now if you go back to the table, okay, let me choose another color. So now I have to subtract 666 here. Okay, because I know that V5 direct sum 6 is sitting inside V. To get that, I need to delete this 6, but here 8 is there, so I delete only 6 here. So -6. Okay, and then this will get deleted. So now you can see if V5 appears 6 times in V, but still some multiplicity of -1 and 1 is there. But what are all the possible maximal eigenvectors? It can be odd or even. Okay, it can be 5, it can be 4, it can be 3. We have to see what are all the possible. But the thing is, the eigenvalues 5 and 3, both of them are having same weight spaces, same dimensional weight spaces, 6, 6. So 3 cannot be maximal again. Because if 3 is maximal, then that will give you disjoint copy of V3 inside. Na? Okay. Suppose 3 is maximal, then V3 has to sit inside V. So that means it will give you disjoint, another set of weights that will add here extra dimension. Okay. So that means this cannot occur. So this can be deleted. So now by this analysis, you can see that V5 occurs 6 times, and then you have V1 now, because if you go to here, you get 2 here, another 2 here. So 3 is not maximal, but 1 is can be maximal. So there are two dimensions left there. Okay, so that can be used here. Then that will actually give you 2 copies of V1. So this is taking care of all odd weights. Now if you take the even weights, then you go to the max here. What is the max? Max is 4. So you have to start with the top and then come down. Okay, then only you will be able to find how many irreducible components can be there. If I take that max 4, then you can see that it occurs with 2 multiplicity. That means I can have V4 twice inside V. Okay, but if I take V4, what are all the weights? -4, -2, 0, 2, and 4. Okay, but each one of them occurs twice because V4 direct sum 2 is already appearing. So then I have to delete this. I have to delete this, and here I will put -2, and I will put here -2, and then here -2. So basically, what remains? So this one is getting cancelled. 1, this is 3, and this is not there. This is already 0. This is 2. Sorry, 1, 1. So this is 1. Okay, so these are all the remaining things. So then again I can start with after 4, what is there? 2 is there. Nah? So whether 2 can occur as maximal, yes, it can occur because V2 can be there because this 1 is there. That 1 is going to give you 1 maximal 2 weight space. So that means I can take 1 here, V2 here. Okay. So then I'm subtracting this 1 here, and then this 1 will go away, then 2 will be here. So then that is going to give me, so this is also going to get cancelled. So then the remaining thing, so after 2, it is 0. So 0 is going to give me here, 2 of them are there, so I can add 2 of them here, V0 twice. Okay. So this is the very explicit decomposition of capital V given this information. So what is the thing? So V0 occurs twice, V1, and then after that V2 occurs. So V1 occurs twice, V2 occurs once, and then V4 occurs. V3 doesn't occur. Okay. So V4 occurs twice, and then V5 occurs, but V5 occurs 6. So that is how you calculate the multiplicity of irreducible representations of this capital V. So now, what are all the answers? If you go to the question number 4, the multiplicity of V0 is 2. So that is there. So it's correct. So A is correct. If you take the multiplicity of V3, so it says it is 1, but so that is not correct. Because multiplicity of V3 is 0, so B is not correct. So now if we go to C, multiplicity of V2, that is 1. Yes, it's correct. And then the multiplicity of V4, that is actually 2, it is given 4. So B is not correct. So only A and C are correct. Okay. So this takes care of A, and then this takes care of C. So is it clear how to get the decomposition?
Yes, sir.
Yeah.
Actually,
So you have to
I did.
start with the maximal and then come down one by one.
Yes, I also doing like that, sir.
Ah,
But as in you thought in video, I go with that whenever um, uh, that uh, the irreducible representation we are is not equivalent to that means now
okay. Are you comfortable
okay.
in Tamil? You can talk in Tamil, not a problem.
Yes, sir, thank you.
Yeah.
Sir, இல்லைங்க சார் இப்போ வந்து வி ஃபைவும் வி
Mhm.
த்ரீயும் காங்க்ரோன் மாட் டூ வரும்.
Correct.
Yeah, correct. Yeah, that's correct.
ஸோ அந்த ப்ரொசீஜர் நம்ம அப்ளை பண்ணோம்னா நீங்க நடத்தும்போது சொல்லியிருந்தீங்க ஃபர்ஸ்ட் மேக்சிமம்ல இருந்து போகும்போது
Mhm.
சப்போஸ் அந்த V5 N1 காப்பீஸ் இருந்ததுன்னா அதனுடைய மேக்சிமல் வெயிட் ஸ்பேஸ் n டைம்ஸ் இருக்கும் டைமென்ஷன் ஆஃப் த ஹெச் ஐகன் ஸ்பேஸ்.
Yeah, exactly.
அதுக்கு
It
N1
is,
காப்பீஸ்.
yeah, it is 6 here. So that is why V5 occurs 6 many copies. Yeah.
எஸ் சார். அண்டு 3 பார்த்தோம்னா இப்போ காங்க்ரோன் டு 5 மாட் 2.
Mhm.
ஸோ நம்ம என்ன பண்ணுவோம்னா நெக்ஸ்ட் 3னுடைய ஹெச் ஐகன் ஸ்பேஸ் அதுல இருந்து சப்ராக்ட் பண்ணுவோம்.
Yeah, exactly. Yeah. Mhm.
ஸோ இங்க
இங்க 6 தான் இருக்கு. Okay, we
ஆமா.
have only 6 here, but there is already 6 coming from V5. So if you subtract, there won't be anything left. So it will be
Yes.
only 0. So because it is just 0, then we can't have V3 copy. V of 3 copy inside our SL2 representation capital V.
எஸ் சார். ஸோ V3 இங்க நம்ம டீகாம்போசிஷன்ல வராது சார்.
Yeah, exactly. Yeah.
இப்போ அப்படியே அந்த ஈவன் கேஸுக்கு வந்தோம்னா 4 4 வந்து மல்டிப்ளிசிட்டி 2 இருக்குங்க சார்.
Exactly. Yeah.
நெக்ஸ்ட் 2னுடைய மல்டிப்ளிசிட்டி வந்து 3 இருக்கு. நம்ம 3ல இருந்து 2 சப்ராக்ட் பண்ணிடுவோம்.
Yeah. Exactly.
Because 4 and 2 are congruent mod 2. Same as 0 congruent to 2 mod 2 and 0 congruent to 4 mod 2.
Yeah. Yeah. Exactly.
ஸோ இப்போ வந்து இந்த கேஸில் வந்து ஐகன் ஸ்பேஸ் ஆஃப் 0னுடைய டைமென்ஷன் 5ங்க சார்.
Yeah.
ஸோ அது வந்து போத் V2 அண்ட் V4லயுமே கான்ட்ரிபியூட் பண்ணியிருக்கோம் அந்த 0 ஐகன் ஸ்பேஸ்.
Exactly.
ஸோ அந்த 2 ஐகன் ஸ்பேஸ்ல இருக்கிற மல்டிப்ளிசிட்டியை ரிமூவ் பண்ணிட்டு ரிமைனிங் இருக்கிறது மட்டும்தான் சார் நமக்கு அந்த V0ல இருக்கும்.
But you have to come from the top. Okay. First you have to go to the V2.
Okay.
So அப்போ வந்து first if you subtract the 2 in the dimension of 3, okay, அந்த 2 ஓட dimension வந்து 3 இருக்குல்ல.
Yes,
So
sir.
here the 2 has dimension 3. So this 2 contribution coming from V of 4. Okay. So
Yes,
when you
sir.
subtract, you will have 1 remains here.
Okay.
So that 1 is what is going to give you maximal vector for V of 2.
Okay.
Okay, அதனால we can make sure that V of 2 copy is there. That is why I wrote here V of 2 copy.
ஓகே தாமோதரன், நீங்க வந்து ரெண்டுத்தையும் சம் பண்ணிட்டீங்களா? 3 + 2
நான் சப்ட்ராக்ட் பண்ணிட்டேங்க சார். டைமென்ஷன் ஆஃப் V0 ஐகன் ஸ்பேஸ் அந்த V0 மைனஸ் டைமென்ஷன் ஆஃப் V2 மைனஸ் டைமென்ஷன் ஆஃப் V4.
ஸோ V2லயும் V4லயும் இன்டர்செக்ஷன் இருக்கும். தட் இஸ்
Okay.
ஸோ V2ல வர V0 ஸ்பேஸ் வந்து V4லயும் 2 தடவை இருக்கும்.
ஓகே ஓகே.
ஸோ இது வந்து யூ ஷுட் திங்க் ஆஃப் இட் அஸ் பீலிங் ஆஃப் ரெப்ரசன்டேஷன்ஸ். மேல இருந்து ஹையஸ்ட் ரெப்ரசன்டேஷன் வந்து நீங்க உரிச்சுக்கிட்டே வரணும் ஒன்று ஒன்றா. ஸோ 4 வந்து நீங்க 2 தடவை உரிக்கலாம். உரிச்சிங்கன்னா 4ல எதுவுமே இருக்காது, 2ல ஒரு காப்பி தான் மிஞ்சும், 0ல 3 காப்பி மிஞ்சும். அப்படி பண்ணீங்கன்னா உங்களுக்கு இன்னும் கூட தெளிவா இருக்கும்.
ஓகே.
So
It is clear now.
நெக்ஸ்ட்
yeah,
அந்த டூயல் ரெப்ரசன்டேஷன் ஃபைண்ட் பண்ணு.
dual
இந்த வீக் 7th வீக்ல செகண்ட் क्वेश्चन கொடுத்திருந்தோம்.
okay, V1 tensor V3 dual.
எஸ் சார். இப்போ ஜென்ரலா இப்போ விஎஸ் நம்ம வந்து டைரக்ட் சம் ஆஃப் இர்ரெடியூசிபிளா எழுதிடுறோம் சார்.
Okay, V1 tensor V3 star, and then it's again given something like you take this direct sum V of 0 star tensor V of 2. Okay. Yeah. What is the question? So you start with V3, yeah?
இல்லைங்க சார், ஜென்ரல் டவுட்டுங்க சார்.
Yeah.
விஏ நம்ம டைரக்ட் சம் ஆஃப் இர்ரெடியூசிபிளா எழுதிடுறோம் சார்.
Okay.
இப்போ அதே மாதிரி பி டூயலையும் நம்மளால இர்ரெடியூசிபிள் ரெப்ரசன்டேஷன் ஆஃப் SL2C எக்ஸ்பிரஸ் பண்றோம்னா ரெண்டுக்கும் ஏதாவது ரிலேஷன் இருக்கா?
There is a relation, obvious relation. So if I take the dual, if I take V direct sum W, the dual actually will behave. So what will be the dual of this? So there is the natural whatever guess will be there, na?
Dual of V.
Yeah, it is just a direct sum of the duals.
Direct. Yes.
So it's actually like more clearly, if you want to write, it has to be written this way. But then you already know that this is same as V dual direct sum W dual. So V direct sum W is isomorphic to W direct sum V. Okay.
Yes.
When you take, it will switch. But anyway, that is the natural map that you are going to give. But it's not that hard to prove that V direct sum W star will be same as V star direct sum W star. There are many ways to actually see this. You can actually just see at the level of the character. We already proved, now at least for SL2 representations.
Yes.
If the characters are same, then the representations are isomorphic. Na?
Yes.
So now, if you just look at the character of these things, you can easily prove they must be same. So first of all, if I take V, if I write it as some direct sum of, let's say, irreducible representations. So V of K1 direct sum R1 direct sum, etc. Let's say direct sum V of Km R. So if you write it as direct sum of irreducibles like this, okay, then to compute using this thing, so you want to climb V star, what it is. So if I want to prove this, then basically you are climbing V star to be V of K1 star, and then you want to take direct sum R1 times. Nah? Okay, V of Km star direct sum R1 times. But do you know what is V of M dual? It's easy to actually see what it is. Do you have any guess?
Actually, I found for V3 dual for last problem.
Yeah, but VM dual, can you guess what it can be?
Okay, Damodaran, here is a simpler question. What is the dimension of VM dual?
M plus ones.
Yeah, but how many irreducible representations are there of dimension m plus 1 up to isomorphism?
Only ones.
So then that says this has to be V of m.
But whether that dual representation is also irreducible.
Yeah, that is a good question. So yeah, you take it as exercise. So basically, you have to prove something like this.
I found for V3 dual, sir.
So there is this very natural inclusion. Suppose W is a submodule of V, okay? Let's say SL2 sub representation, okay? So then you can actually prove that. So it's, you can extend now, like how do you extend? You want to go to the dual, huh? So there is a restriction. So the restriction will be okay. If you have a map like this, okay, W to V. So this is the map. So this is the inclusion. So now what is the dual? Dual is home V comma C. Okay. So now if I give you a map from V to C, let's say some functional, then with this I can associate F restricted to W. So which is a map from W to C. So if I think about this map, then you can see that there is a map from V star to W star, which is again mapping like this. Do you see this map? So this is actually inclusion. Okay, this is injecting. W to V, you have injective map. Then from V star to W star, you have a surjective map. So this is injective map, and this is surjective map. But we are already proved something. All finite dimensional representations of SL2C, they are all completely reducible. Okay, so that means if I give you any exact sequence, that is actually what? Split exact sequence. Nah? So if I have W, V, then you have the quotient V mod W. If I have something like this, then V can be written as isomorphic to W direct sum V mod W. Okay. So now if I take V dual to W dual, I have the surjective map. So I will have the kernel of this, whatever this. So then we know that V dual is going to be W dual direct sum the kernel of pi. So this simply says if W is a sub-representation of V, then W dual is again you can think of sub-representation of V dual. So that forces that if V is irreducible, if and only if V dual is irreducible. So it's basically playing around with the maps. Okay.
Okay, okay. I whether I made a mistake.
So only check this much. Okay, you have to check given F, you can define this F restriction. So that is the map. F goes to F restriction W. So I'm saying this is a surjective map. So that is just follows from any basis of W can be extended to basis of V. So that means any linear map on okay from W to C that indeed comes from some linear map of V from C. So that is the meaning of this is surjective. If you just think about it, it's just yeah, basically like yeah, one simple exercise. But
Okay.
through that, V is irreducible if and only if V star is irreducible. Okay. So V star star will be isomorphic to V naturally. So that is from linear algebra. And that natural isomorphism is actually SL2 isomorphism. So now using that, you can actually say easily now V of M star is V of M. Okay. But otherwise, one other way to look at it. So if I write H eigenvalues, what it will be? If I take H eigenvalues of V of M, you know what are they? Na? What are they? It starts with minus M and then goes all the way to
M plus.
M minus 2M. So this is the H eigenvalues of V of M. Now I will leave it as exercise. This is very simple exercise. If you take, if you compute H eigenvalues of V of M dual, okay, so this is just going to be flip of this M, M minus 2, etc. M minus M plus 2 and then minus M. So basically the dual of this is going to be this. Okay, basically the dual here, if I take V of V minus M, then that will map to VM. Now you can use the information about SL2 modules. Na? If you have such eigenvalues and all of them have dimension 1, then that must be irreducible. Okay, and that is irreducible corresponding to the dimension n of that module minus 1. So this is something you can just try to do. The dimension of V M star like this I is going to be 1 when I comes from M to minus 1. You got it? So now if you go back to the exercise, it's easy. Actually, now you can simply look at, you have to count again the all possible dimensions. Now, whatever the techniques that you learn, the peeling off one by one from the maximal thing. Okay. So now if you go to this V of 1 tensor, V of 3 star. So this is naturally isomorphic to V of 1 tensor, V of 3. But V of 1 has what? Minus 1, 1. V of 3 has minus 3, minus 1, 1 and 3. So now if I take the product, then what will happen? So then you can write down very explicitly what will happen. So you can prove this is indeed isomorphic to V of 4 direct sum, V of 2 direct sum, V of 0. Sorry, is it correct? 4, 2, and then you have to go m plus n up to mod n minus 1. There is no- V of 4 because this 3 and this 1 will give you 4. Okay. So this 3 and this will give you 4. So then, yeah. Hmm. Yeah. So only the 1 will have like 2 dimensions of product. Okay, this is something you can just do it from by counting the dimension of the eigenspaces. So it's V4 direct from V4. Any other questions? Actually, there is a general rule. Okay, it is mentioned in exercise of Humphreys. If I take Vm tensor Vn, then you can prove it is isomorphic to Vm plus n direct sum Vm plus n minus 2 direct sum etc. direct sum V of mod n minus 1. Okay, this is again you can do it by looking at the dimension of the H eigenvalues, H eigenspaces. You can assume n is greater than or equal to n because this is same as V of n tensor V of m, and then you can just replace this with n minus n. Okay, Damodaran, do you have any more questions?
But only one doubt.
Yeah.
Actually, I work with the a dual basis for the irreducible representation V3, sir.
Okay, so then
Uh,
you will be able to prove this eigenspace thing, na?
I find the action of SL2 on this basis, sir.
Mm-hmm.
From that, I got uh, uh, that dual basis F0,
Yeah,
F1, F.
if we use dual basis, then this exercise is easy. Computing the eigenvalues will be easy.
But whether I made a mistake or but from this I decompose V3 dual as V0 and V2. It's done.
No, 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 it is not correct. It has to be V3. So if I start with V3, you have what? Minus 3, minus 1, 1, 3, na? So you label them as V minus 3, V minus 1, V1, V3. So maybe your definition of dual basis may be not correct. So
Actually,
you will
3
have
is
F minus 3, F minus 1, F1, F3. What is the dual basis definition? Fi of Vj has to be
del H.
delta H. Okay. Now, if you compute the H eigenvalue, H dot Fi, so then you will be able to prove this I is what, like it will become M minus I. It has to be M minus I. Yeah, that's so let's do it for okay one example. Okay, so let's compute H dot F1. Okay, because this one I'm taking. So H dot F1 of, if I compute anything else, then what will happen? Like if I compute Bj, so this is by definition is what? Minus F1 of HVj, na? Okay, this is minus. So HVj is going to be what? Whatever j, that j is going to come out. Okay, F1 of JVj. Okay, so then this j comes out minus j F1 of Vj. But F1 of j times F1 of Vj is going to be what? That is the question. So F1 of Vj is the delta 1j, na? So it's going to be multiple of F1 only. Okay. So you have to,
One has to take the
no, but F1, you have to write it as F1, the operator F1. So now using this, okay, maybe what I wrote here is not correct. This is just a minus. Yeah. So you have this operator, okay? F1 H dot on Vj, it is acting as minus j F1 of Vj, which is nothing but minus j delta 1j. From this, I'm asking what is this operator? So this operator is going to be exactly minus F1. Because F1 of Vj is delta 1j. So minus F1 of Vj is going to be minus delta 1j. But when j not equal to 1, it is going to be 0. Otherwise, it's minus. Okay. So this is same as minus j delta 1j. So once you know how it acts on the basis, you know how it acts. Huh? Okay. So maybe the what I wrote there is not correct. It's a minus of. But that is what I wrote there actually. The minus only I wrote. Huh? So if you take minus m, you get m. You get minus m plus 2, you get m minus 2. So this is the thing you have to observe. Okay, so any more questions? So there is one new addition, Himanshu. So Himanshu, you have any questions?
Yes, sir.
Yeah.
Sir, in the assignment 7, question number 7, sir, where, sir, it is written that the diagonal part of uh, upper triangular matrix is semi-simple in the Jordan-Chevalier decomposition.
Upper diagonal of Jordan Chevalier. Okay.
So, sir, I am not able to understand why this is not true.
Okay, so it's because a diagonal matrix need not commute with an upper triangle matrix, strictly upper triangle matrix in general. But
Uh,
the semi-simple part and nilpotent part of Jordan Chevalier decompositions will always commute.
yes, sir. Yeah.
That is the reason. So I
Uh,
think one can easily give an example.
yeah. Okay, sir.
Yeah. If
Yeah. Yeah.
that
Okay.
is scalar, then yes, the answer will be. But diagonal need not be scalar. Okay.
Mm. Yes, sir. Okay.
Any other questions? Okay, so if you have any more questions, you feel free to write to us. Okay, no issues. So we will be answering. So you can also write it in the discussion forum. So the tutors will be happy to write. Or otherwise, you can also email me, not a problem. Okay. So if there are no more questions, then shall we wind up this session?
Thank you.
Yeah.
Thank you, sir.
Yeah. Thanks for being here. Thanks. Okay. Naveen, are you there? Okay. Okay then. So yeah. Thanks everybody. Yeah. You can leave now. Yeah. We will also leave. Let me just check that YouTube has any questions. Okay. YouTube doesn't have any questions. Yeah, we can end the session. Thanks.